characteristics of phase separation, right? So let's say we have a temperature like this, and then concentration here. Then we have the coexistence curve like this. This is for UCST, and the spinodal curve is like that. And we said this is unstable. This is unstable. And in this region, it's a metastable. And also in this region, it's a metastable. Okay. So let's assume, very similar to the question you asked earlier, let's assume I prepare a solution here, right, at that point, that is in the homogeneous phase, above the critical temperature. Okay, so this is the critical temperature. Okay, and this is, of course, a phi critical. Right, let's prepare a sample somewhere here and then quench it. If you quench it through the critical point, you get in here into the unstable region. Or instead of this, suppose I have, in the homogeneous phase, I have a solution with this concentration, average concentration is somewhere here. Then I quench it, right? Then I'll get into this metastable region. Depending upon whether I quench the system into a metastable state or an unstable state, the mechanism, how they are going to make, the system is going to make the two daughter phases, the final phases, is going to be different. For example, right, suppose I quench the system to this temperature, right? Then I would say eventually it would be phi prime. Let's say this is phi prime. Let's say this one, right? And this is phi double prime. Let's say that. Okay. Suppose I quench it to that temperature, I will have two phases, one with this concentration, the other one with this concentration. So let me draw a cartoon of this, right? The cartoon, suppose I have a mixture and I'll put dots for only one component. Okay, the rest of them are the other component, right? So this is the concentration of, this is phi, that represents this phi. So I created a solution, say either here or there, right? In the homogeneous phase, there is some concentration. Let's assume the concentration here is phi E, that's the equilibrium value. Then once I quench it, right, what will happen is, if I take this for time, this is time going to infinity, what you will have is the following, as you know. So I told you there is a phi double prime and phi prime. That's what will happen eventually. No matter how, where I quench it, whether I quench into the metastable region or unstable region or this metastable region, independent of that, as the time goes to infinity, I will have two phases. One phase would be more, this is a phi double prime, because the phi double prime is higher, right? So this is a phi double prime. And then here it will be phi prime. Here it would be dilute phase. Like that. So this is the final state. So I have an average concentration here, and eventually I'll have two phases. One has a concentration of phi prime, other one has a concentration of phi double prime. So the way we talked about in the last lecture, right? So, in other words, let me draw once more. Suppose I have, so what do I mean by this is this. In this situation, average concentration of phi E, therefore let me plot a phi as a function of a spatial coordinate R. Right? So the average concentration somewhere here. This is my phi E. But yes, this is at a high temperature, right? There is some fluctuation there. Yeah, it will be in general, it will be something like this. The local concentration would fluctuate a little bit, but not too much at temperatures higher than critical temperature. But eventually, this fluctuation should be such that when you get into this state, right, time going to infinity, the density profile, so a concentration profile as a function of this spatial coordinate r would be like this. So this is my phi E. It would not be like that, right? Because that was the average concentration here, but now you're going to have two phases. So one is going to be, say, phi double prime. The other is going to be, say, phi prime. So what will happen is, okay, so you'll have something like this, one phase, it will continue for a while, and then there will be an interface, and then I'll have the other phase. So this interface is this line. The line that I'm writing here is this interface. So this is a dense phase, and this is a less dense phase compared to the average concentration. So eventually what will happen is this. So our question is, how does this concentration variation, fluctuation, very, very small, weak fluctuations, so how do they get into, how do they become fully phase-separated system? That's the question. And there are two ways to do this, right? And that depends on whether I'm starting from here in this region, or I'm starting from in this region or this region, whether I'm starting from unstable region or in a metastable region. That's the way this becomes this profile, depends on the initial state where I create. Okay. In the last lecture, I talked about this region, right? And I want to summarize this because I want to contrast between these two mechanisms, right? So what we did was, in the unstable region, the mechanism is spinodal decomposition. Okay, so what do I mean by that? So let me draw, for this particular case, let me draw what the situation is. To summarize what we did in the last lecture, so let me go back and draw again the density profile. This is R. This is, say, this is, let's assume this is my phi E. Let's assume this is my phi double prime. Let's say this is phi prime. Okay. So at the time equal to 0, right? At time equal to 0, that's what I will have, because I just quenched it. Wherever I suppose I had my mixture here and I quenched it here, at t is equal to 0, although temperature is below the critical temperature, the density profile is going to be something like this. Tiny fluctuations like this, right? That's what will happen. Then, but you know that the system is unstable. When the system is unstable, what happens is it likes to get out of this unstable situation and wants to make this density profile, because this is the final fate. This is the final result that the system will evolve into. So how does this go from, the system go from this profile to that profile? That's, I'm repeating here. How does it go from this profile to this profile? According to the spinodal decomposition argument we made, the fluctuation will grow. There will be a spontaneous fluctuations. So that will go like, it will grow like this. It will start, the system becomes unstable like that. That is at T1. Then at T2, suppose a little later, but still short enough time, these fluctuations will become bigger, as I pointed out. Right? These become bigger. That's a T2. But please notice the wavelength of this fluctuation is the same for the early times. They don't change. That means when you do scattering, the maximum intensity that you get, right, maximum intensity you get, will occur at one particular wave vector. That K max or Km, we call it, would not change, or Qm, depending upon which symbol you use for scattering wave vector, that would not change for early times. But for longer times, as we talked about, right, then you get fluctuations like this. That means that now this is a T2, T3. T3 is much longer, right? But please notice when the fluctuations taking place, they have not reached, the fluctuations do not yet know the equilibrium value of the final phases. They do not know, these fluctuations do not know when they are evolving, right? They don't exhibit the phi double prime or phi prime because these are fluctuations. Of course, eventually, if you wait long enough, this will reach this particular state. This will become bigger and bigger, and then it'll hit that value, right? These are the, this is the value that we are looking for, right? Eventually, it has to come to that way and that way, these fluctuations. So this is the essential qualitative feature of spinol decomposition. Now, let me emphasize certain consequences of this behavior. One important consequence is rate. That is, if I look at a scattering intensity as a function of K and T, this K is scattering wave vector. In your experiments. At particular time, T, you make your system, you quench it into unstable state, right? And then you watch the intensity. That goes for early, well, first of all, I will write this to be, this is proportional to the fluctuation at time T square, where psi is equal to phi at R minus phi E, right? That is, this is phi, this is a fluctuation. Then I do a Fourier transform of that fluctuation, and that gives me this psi of K. That's a Fourier transform of this psi, which is this one, right? This goes like some rate. Okay, please notice that this is rate. This one, rate of growth of fluctuations. That's what you're measuring. This is for early times. For early times. For early times, stability analysis gives you these results. So that means at early time, the scattering intensity grows exponentially with time, right? Grows, right? We'll see how that looks like. Exponentially with the time. And the prefactor of this time is a rate. So that's why I call this omega K to be rate. And we showed in the last lecture that omega K, right, is equal to negative lambda K square times A plus kappa K square in linear limit, the ones and Zenica limit. And I also told you that A is equal to T minus TC. Remember, we did this when we did a Flory-Huggins theory. Here, we are in this particular case. That's how we composed in the homogeneous phase. So capital A is second derivative free energy, according to Flory-Huggins theory, for example, with respect to the composition. So that means for T less than TC, right, A is negative. For T less than TC, A is negative for phase separation here. So based on this, what we argued was that, okay, the rate, this is important. I wanted to really rate. This is the rate. Rate rate of growth of fluctuation. Rate of fluctuation. Rate of growth of fluctuation. Please remember this, right? Rate of, right? Now that is, right, if I plot this as a function of wavelength, right? This is K. K is a wavelength, right? This is proportional to 1 over length, as you know. And then we showed this because here A is negative and this is a negative sign, right? Then it went like this. And then we said, this is a Km, and this is Kc, critical value of K. Below, when K is below Kc, this is positive. Rate of fluctuation is positive, right? If for K larger than Kc, this is negative, right? And then also the maximum of this curve occurs at Km, and we talked about Km going like, what did we do? Km goes like, I forgot the answer. I think it goes like 1 over the square root of T, right? K critical, and that goes like Ts minus T power half. Okay, because that's a quench step. For a spinol decomposition at the critical temperature, Ts, spinol temperature same as Tc. But we are trying to do under the in the unstable region. So this is my Ts when I critical, I mean, this is spinol temperature. I have my homogeneous phase, I bring it here, that's the spinol temperature. And then for T less than spinol temperature, we'll have this, right? So in general, it is Ts minus T power half, that's Km. So the position of this maximum intensity in wave vector space, because if this is rate of fluctuation is positive, it's here. So intensity is going to grow exponentially with the time, but that intensity will be peaked at the Km. Because the rate is peaked at Km, therefore the exponential of that peak will also be a peak, right? Will be a very strong peak. So the position of that peak is dictated by your quench depth, right? So if you have a shallow quench, then I say shallow quench, I'm going, say here, that's a shallow quench. And a deep quench would be from here. From deep quench will be, I'm going all the way deep here. So depending upon how I quench, I go to shallow quench or a deep quench, right? The position where you have the maximum intensity in wave vector space will depend. And you can make a prediction that is going to go like this. This is an important information because you experimentally, you know how much temperature you're going to change. Based on this, you can expect, the position of the peak, where the peak is going to be. So that way you can design your experiment, whether you want to do light scattering or USACs or SACs, depending, right? Once you expect what you are going to get for Km, maximum position, you could design your experiment accordingly. Otherwise, you'll miss this phenomenon. If you are not looking at the right length scale, you will miss the phenomenon. So therefore, that's how these theories are come into handy. All right. Okay. So then I want to make one important remark because this is a hotly debated argument, particularly in a polymer crystallization community. All right. Let me look at, according to this mineral decomposition, let me look at the rate of fluctuation again. Rate of fluctuation again, right? So let me write this to be omega k in the linear analysis, omega k. So I have, okay, divide this by, say, lambda k square. I take this and divide by this. Then I have that's equal to minus a, right? Negative. I divide this left-hand side by lambda k square. So therefore, negative a, negative kappa k square. Okay. And this is equal to, as you know, negative a is negative. Negative a is a modulus of a, the magnitude of absolute value of a, minus kappa k square. So this means if I plot, I experimentally measure, go to the laboratory, I have a system, some unknown system, and make a measurement of the scattering intensity as a function of scattering vector k. Then what I do is from that, let me see whether it looks exponential. If it's exponential, I can get the rate. I can find the rate. And then I take the rate divided by k squared. I know what k is. I know my scattering angle. I know the wavelength of the incident beam. So I plot this quantity, omega k by lambda k squared, as a function of k squared. Suppose I plot as a function of k squared. What you will see is, based upon this result, is you have that quantity that is intercept, modulus A, and please notice it's a negative sign, and kappa is a interfacial tension, right? And that's a positive. Therefore, what I'll get is, I'll get a straight line like this. And then that slope is related to kappa, but it's a negative, right? This gives, so they are actually, according to this plot, it's exactly minus kappa, right? But I get the information about kappa, but the important thing is the rate divided by k squared as a function of, as a plot of k squared is a straight line like this. This is a symptom of spinodal decomposition. People use this whenever you see this, you say, "Oh, it's spinodal decomposition." Right? But please notice that this is not equal to a situation. It is not equal to a situation where, if I plot omega k by lambda k squared versus k squared, suppose I get a curve like this. Suppose I get like this. Yeah, I get a straight line there, okay? But here I have these things coming in. That means this is not the same as this. So if you get something like this, we cannot say that it's spinodal decomposition. If you want to have spinodal decomposition, you should be like this. Okay? So, right, when you cannot simply argue from an experimentalist point of view, oh, I have a beam stop, therefore I'm going to throw away this data. We can't do that. Okay, we should not do that. Once you see this upturn, then no, it's a very clear indication that the phenomenon is not spinodal decomposition. Okay? Because this is, I know that Professor Liang Bin Lee's group, a lot of experiments are going on, and I want to make it very clear how to analyze the data. Okay. Now, I told you how, this is a summary of what I did in the last lecture. According to the spinodal decomposition mechanism, fluctuations spontaneously grow, right? And then you have this behavior in the early regime, you have this behavior. And if you wait long enough, as we talked about K max, if you wait long enough at later times, Km comes down as time goes up. Okay, and I also told you log Km versus log T, right? In the early regime, this is here. It's Km does not change with the time. That means the slope here is 0. That's the early region. And then I told you that a little later, it becomes something like -3 slope, and then eventually it will become -1. Which I -1/3, sorry, -1/3, I misspoke, here is -1. Okay, this is intermediate regime, and this is our late regime. Sometimes people call this to be late regime, and this is very late regime, right? And that's the way Km evolves with the time. Please notice when I go to very long times, Km is small. When Km is small, that means what? That means length scale is large. That means I'm here. I'm here. Okay. In fact, what will happen is when you go to very late stages, right, there will be a merger, right? If you go back here, if you look at the density profile, eventually much later times, this will hit the maximum value. This one will hit the maximum value. This one will hit maximum value. Then they have to, different domains have to collaborate to make these two daughter phases. Okay. Now, this is what happens in this region. Now, what I like to do is I like to tell you about what happens in here. Suppose I quench the system into the metastable state here in this region or in this region, right? Now, what happens there? Now, oh, okay. So let me very quickly tell you right away, and then we'll do the analysis later. What happens, please give me 2 minutes, right? What happens here is, again, so let me start. Okay, this is phenol decomposition. Let me go to nucleation growth. In the metastable region, we have nucleation and growth. That's the mechanism. Okay, so once more, I'm going to remind you again, our goal is how does a system go from here to there, right? This is where I start from, right? How does it go from here to there? The way it does is in this mechanism, so here is R, this is my phi E, so this is my starting point, right? This is T is equal to 0. Maybe I'll make it longer. This is T is equal to 0. This is R. Oops, sorry. Right? Now, in this mechanism, as soon as I make, this is my equilibrium value, phi double prime, and this is phi prime. Let me consider one phase. What happens is, spontaneously, with spontaneous is not the right word. If you give enough energy to the system, it immediately makes a daughter nucleus, embryo. Okay, that means what? This is already, this is some domain, some droplet here, but the concentration of that droplet is equilibrium concentration. And not only one, maybe there are several of them with different sizes. Let me draw like this. There's another one, maybe even a tiny one like this. These are nuclei. These are called nuclei. Yeah, nucleus here, another nucleus here, another nucleus here. Nucleus of your daughter phase. And this is the mother phase, right? The background is the mother phase, right? This is the mother phase. This is a daughter phase. This is a daughter. This is a daughter of one phase, right? And a little later, if I wait a little longer, what happens is, okay, this will grow. It will become bigger. This will grow bigger. And this may become bigger or may even dissolve back, right? This is for T2. And the previous one I wrote down, this one for T1. Okay, and this is what we're going to talk about during the break. In other words, what I'm going to say is instead of this kind of fluctuation I told you here, right away, your nucleus of a daughter phase is born, one or many, right? That means in terms of pictures, what I'm going to draw is the following. Suppose I start here. These are the molecules, right? As a function of time, what happens is, yeah, droplet, let's say that droplet is born here. Okay, and another droplet is a bigger one. Okay, that's born here. Right, and another tiny one, so that's born in here. Right? But inside this droplet, the concentration, the equilibrium concentration. Okay, and then eventually, of course, if you wait long enough, I have my usual case. This is one phase, one complete phase, phi double prime, and here is a phi prime, a dilute phase. So this mechanism is called nucleation growth. The nuclei are born and then they will grow, which this is what we're going to discuss after the break. So let's take 5 minutes break right now. Is that okay? Okay, so I started with the phase diagram for UCSD system as an example. This is temperature versus volume fraction. And here is our coexistence curve. And this is our spinodal curve. And we were trying to consider the mechanism of phase separation. And here it is TC. And what we are going to do is we are going to quench the system into here. I start from here, say, at homogeneous phase, and then I bring it down here. Right, that's what I do. I bring the system there. And at that temperature, I'll call that to be, this is actual temperature, right? Where we are going to make measurements. And we know that the equilibrium after the process phase separation is over, I should get a phi prime and phi double prime, right? And my initial composition is this. That's my initial composition. That's my phi, right? And let's look at, I already mentioned to you in the last lecture, suppose I plot phi as a function of location. This is the location, spatial location R, and the starting composition is somewhere here. That's my starting value. And let me call this to be phi, right, at that point, at the phi equilibrium or something like that. And we know that in the spatial location at finite temperature, it is fluctuating a little bit, like that. This is at T is equal to 0. Then as soon as the phase separation will take place, if you wait for some time, what will happen is right away, you will make a nucleus. Where the concentration of that nucleus is phi double prime. Already it's a bulk value. Okay, and at some other locations, spontaneously, again, spontaneously means without any, without a continuous growth of concentration, right? It'll make another nucleus of a different size. So this corresponds to T is equal to 1. The blue color corresponds to T1, which is larger than T0, of course. This is T0. Okay. And then what happens is, little later, this nucleus will grow. This nucleus will become bigger, like that. See, this is the size. This is the size of the R, spatial, okay, the size of the droplet. So this is, similarly, this will also become bigger. This is at T2, which is greater than T1. Eventually, of course, right? Eventually, of course, what will happen is you will have phi of R, and then you have one phase. This is a phi double prime, and then there's an interface, and then this is phi prime. Two phases will phase separate, will coexist. Now, this is what we call, this is a nucleation process. What we call is, right, when you do something like this, I could probably draw another cartoon like this. To begin with, there are some droplets that are born, created, nucleated, and then another small droplet. Please compare this with the spinol decomposition. In spinol decomposition mechanism, you do not make the daughter phase. That phase is, the concentration of that phase is this. Or you could also think about the mirror image of this. You could also make droplets of this phase, 5' phase. But the important thing is that the daughter phase has the equilibrium concentration, which is a concentration eventually in the phase separated system. In contrast, I'm going to write it and I'm going to erase this. Instead of this situation, in the spinol decomposition case, what you had is, remember this, phi, right? To begin with, it's like this, t is equal to 0, and then there's a fluctuation like this. And then these fluctuations will grow like that. And then they grow like that, right? And only at very late times, you get the final concentration. This is a spinol decomposition mechanism. In contrast, in nucleation growth mechanism, you make these nuclei like this, okay? Where the concentration inside the nucleus in the droplet is, or your nucleus is the same as your eventual thermodynamic value. Okay, that's the difference between nucleation growth. This is a nucleation and growth, N and G, and here is spinol decomposition. Compare. That's the physical picture you should have. Okay, given this, we are going to now describe how the nuclei are born. Okay. Colloquially, what people say, we like to say, is the following. Okay, so here I have mother phase. We call this to be mother phase, which leads to the nuclei. Mother phase, which is this one. And then these are called daughter phases. This is daughter, colloquially. In the literature, that's what you will see. Okay. So now what we are going to do is we are going to talk about how these nuclei are born. We had a good discussion about the spinol decomposition mechanism, right? We had, let me remind you again, because I don't want you to, here is an example. In the spinol decomposition mechanism, right, we worked it out. So look at this, right? Again, that's a starting point, and then eventually you'll get the two phases, phi double prime and phi prime. But then the fluctuations were responsible, right? Eventually, right? These fluctuations, they were growing with the time, and then we figured out that is the rate of growth of fluctuation, rate as a function of k. This is scattering wave vector k. That rate had a maximum, right? So therefore, the intensity will show a maximum, scatter intensity will show a maximum at a certain value of Km, which is related to the quench depth. K maximum would be 1 over square root of 2 times Kc here. 1 over square root of times Kc. Kc is the square root of the quench depth in temperature for the UCSD system. So that's what we did. In contrast, we are going to discuss this problem, the nucleation growth problem. Okay. Okay. How do we describe this? So let me go and draw a cartoon again. Okay. So what I'm going to do is consider, right, formation of a droplet. Yeah, spherical droplet. Why do I want to do spherical droplet? To just illustrate the simplicity of the argument. And once we know how to do for spherical droplets, we can do for any morphology. When we talk about lamellae in polymer crystals, or even liquid crystalline situations, or even birth of galaxies, you know, in cosmology, we can use lots of same idea, exactly same idea, but the details will be different. But so I want to make sure we understand how to do this in the simplest situation, then all of us can do for more complicated situations, for anisotropic objects, fibers, or the birth of fibrous nuclei, etc., etc. Okay, so that means what? That means I'm going to take a droplet like this, right? This is formation of a droplet like this. Let's say the radius of this droplet is r. And remember, when I make a droplet like this, right, I'm going to do this phi double prime. I'm putting dot for every molecule. You know, every molecule could be a polymer chain. Each point here could be a polymer chain or a rod-like molecule or a small molecule, right? And compared to the mother phase where I have concentration like this. Okay. Now the free energy of formation of this droplet, this is a free energy to form a droplet of size r. Free energy to form a droplet of size r. What is that? First of all, compared to this mother phase, the condition, experimental condition is such that it is going to make a new daughter phase, because we know that experimental condition is such that I'm bringing the system in here, therefore it's a metastable, right? The system is metastable, and eventually it will get to equilibrium. That means there's a driving force, right? And the driving force is the chemical potential in the daughter phase is more favorable compared to the chemical potential in the mother phase, right? So we write this to be equal to, right? The free energy should be getting lower, right? Negative, right? Let me write, there is a volume here. So I write 4 by 3 pi r cubed. Instead of using capital R, maybe I'll use a small r, okay? Because I use r for something else in a minute. Four by 3 pi r cubed. That's r is the radius, right? And 4 by 3 pi r cubed is the volume. And then gain in free energy per unit volume, I write as a delta G. So this is gain. I have observed the sign, the chemical potential per molecule, chemical potential of the component is lower in the daughter phase in comparison with the mother phase, right? Lower. And I have observed the negative sign in here. So this is the gain in free energy or chemical potential, if you like, per unit volume. Okay. And it turns out, as you know, from the chemical potential argument, it turns out that delta G is equal to Tc minus T for the critical quench. Suppose I write delta G in general, yeah, delta G in general, that's my Tc, right? That's the below Tc I'll have phase separation. This is my Tc. Below Tc I'll have phase separation. Therefore, this quench depth, the chemical potential difference, is written in terms of Tc minus T, even though, right, we are talking about off quench. When I say off quench, I'm doing it in here, but still the driving force is a Tc minus T. Please contrast this with the spinol decomposition case. In the spinol decomposition case, the quench depth is with respect to spinola temperature. So only below the spinola curve, you have spinola decomposition. There, the quench depth is Ts minus T. And in the case of nucleation problem, it's a Tc minus T. That is given by delta G. And as you know, Tc for upper critical solution temperature, Tc minus T is positive. Okay, so that is the bulk term. But you know, always it costs free energy to build a wall between one domain against another domain. So that is interfacial tension. In this particular case, we will call it to be surface tension because it's a droplet, the nucleus is the daughter droplet, right? It has some sort of a surface against the background. So let's look at the consequence of that. And that's going to cost energy. So that's going to come with a plus sign. That's important. Surface area is 4 pi r squared, that surface area, times the interfacial tension is sigma, okay? And obviously interfacial tension is a per unit area. This is r square is area, length square in terms of dimension. So this becomes a dimensionless. And here r cubed is the volume, delta is per unit volume, that's dimensionless. The way I have written F is a dimensionless. It's units of kT, if you like, okay? This is in units of kT. This is interfacial tension. Okay. Now let's sketch this graph. What happens is this: when I make R non-zero, the free energy becomes negative. When I increase R, it becomes more and more negative. Therefore, I like to make the daughter phase because that's a driving force. But it is mitigated, that tendency to make the daughter phase is mitigated, opposed by this plus sign. Because if they, right, because it costs free energy to make an interface. And that cost depends upon the radius of this daughter nucleus, right? That goes like R squared. And if R is small enough, right, R cubed is weaker than R squared. If R is large enough, R cubed is going to win, right? So therefore, there is going to be some optimization that needs to be worked out. So let me plot this free energy as we gotten as a function of R. F of R. I'm going to plot this as a function of R. R is now radius of the droplet. As I'm repeating myself here, for small r, this term, the blue term is going to be weaker compared to the red term. Therefore, what it's going to do is it's going to take off like this, quadratically, R squared. The curvature depends upon the interfacial tension. But for large R, this is going to win over this. Therefore, I'll have negative contribution, negative term. So this is plus sign, this is 0, this is negative. So what will happen is for a large R, it's going to crash down like this, right? Sharper than this quadratic term. Therefore, what you get is you get a bridge between, if you plot this function, you get a bridge between them, and that will look like this. That's what will happen. All right. This is please notice, this is free energy. We are not talking about rate as a function of wave vector k that we talked about for spinozal decomposition. Here, it's a free energy in dimensionless units of making a droplet of size r, radius r, as a function of r. So this tells me that if I make an embryo, a baby nucleus of the new phase, daughter phase, of this size r, then in order for it to grow, it's going to be difficult, because in order to grow, it has to climb the hill, because in order to get stronger, it has to go up. That's hard. Instead, it will go down. But on the other hand, if I were somewhere here, if the droplet size is bigger than the value corresponding to this maximum, which I'll write it to be some R critical. If R is larger than R critical, suppose I made a droplet of this size, then it's a downhill process. But then the free energy, it gets lowered if it takes more molecules and grows. So I will have growth beyond this point. Free energy will come down more and more. Therefore, the droplet will grow until it reaches the full macroscopic size. Right. So this is what we call that means we need to create a droplet at least this size RC, critical size. Once you make a droplet of size RC, then it can grow. If you don't make that, it's going to be a difficult process. Of course, there is some fluctuations about it, but in general, in the classical sense, right, there is a critical value of RC below which the droplets will dissolve. So let me write down for R less than RC, droplets dissolve. And then for R greater than RC, droplets grow. Okay? So this is a very general situation. Now what we are going to do is, can we get some idea about what RC is? Even for the spherical droplet, can we get an idea about RC is? Because what we care is in terms of the quench depth. Okay, that's the experimental handle. So we want to be able to tell how hard is it to make a droplet of size greater than RC. And what do we have to do? And also we want to know the kinetics, the rate with which these droplets are going to be formed. That would be called, right? This process is called nucleation. And then that rate with which these nuclei are born is called the nucleation rate. Okay. And also, if you look at this one, there is another quantity that must come to your mind. Okay. How hard is this uphill battle? What is this barrier? Right? There is a barrier here. That barrier, we'll call that to be, you could use anything like you can write, nucleation barrier, but I'm going to write F dagger. F dagger, that's the nucleation barrier. So this is a critical nucleus size. This is a nucleation barrier. F dagger is called a nucleation barrier. And R sub C, critical nucleus size. In this particular case, radius. But if you have a lamella, if you have a rectangular block, parallel pipette or something like this, right? And then you'll have, it will be called size. You'll have different dimensions. Okay, how are we going to do this? This is easy because, this is a maximum. So I'm going to find the value of R at which Fr is a maximum. And that we do by taking the derivative of f of R, take this function, take the derivative of this with respect to R, little r, and equate that to 0, then that will give me my R sub C. Once I have figured out what R sub C is, I take that value and plug it back in here. And then if I do this gives me the free energy at that value of RC, which is our nucleation barrier. So let's do this calculation, because this is an important calculation to do, particularly since this comes again and again. Okay, so I write, once more, I write FR is equal to minus 4/3 pi R cubed delta sigma plus 4 pi R squared sigma. So dFR by dr is equal to negative 4 pi R squared delta sigma plus 8 pi R sigma, and I'm going to equate it with 0 at RC. It is 0 only when R is equal to RC. Okay, so 4 pi is a common factor, right? 4 pi is a common factor. This is 0, that goes away. So RC is a common factor. So what you get is simply RC is equal to 2 sigma by delta G. okay? And delta G is quench depth. Therefore, this goes like 1 over Tc minus T. Right? Please notice the physical implication of this. This is a very general theorem. For the nucleation phenomena, if your quench depth is small, that is, you just lower the temperature only a little bit below the critical temperature, but in the metastable range, the RC is very big. When I say RC is very big, this RC is way here. That means most of the times you are making a droplet, they're going to come back, right? They're going to come back, right? But you know, in this picture, right, you know that the free energy, eventually the free energy is going to be somewhere at the bottom here of the mother phase, of the total phase, new phase. But you are starting here. This is why we call this a metastable situation, right? Here is a metastable, it crosses the barrier and eventually reaches the final equilibrium state. That's why the nucleation process is getting out of a metastable state. But the important thing is when the quench depth is very shallow, the extent of metastability is extreme. So it's extremely long-lived. But on the other hand, if the quench depth is strong, that is when you go to lower and lower temperature, then this becomes a larger because Tc is fixed. This becomes larger. Therefore, the droplet size becomes smaller. Now let's look at the barrier. I take this expression, put it back for the barrier. That is F dagger. F dagger means that is F, this is equal to F at R is equal to R sub C, which we just calculate. If we do this, let's do the calculation again, because once you get this, you'll be able to do this as many homework problems as you wish for different kinds of morphologies, fiber formation, collagen bundle formation, polyethylene lamellae, etc., etc. You can do for any system that you want to do. Let's do this. So I have negative 4/3 pi 2 sigma by delta G cubed delta G plus 4 pi 2 sigma by delta G squared, right, sigma. This turns out to be, you can work out the arithmetics, and you can count. There is sigma cubed here, here sigma cubed, sigma squared, sigma cubed. I have delta G cubed in the denominator and delta G here, therefore delta G squared in the denominator, delta G squared in the denominator. So clearly, from physical point of view, you'll get sigma cubed divided by delta G squared. And then you can work out the prefactors, and that prefactor, if you do the calculation, that's trivial. You get 16 pi over 3. So this is my nucleation barrier. So the nucleation barrier goes like 16 over pi over 3. That's a number which is specific to the geometry of your object, right? Sphere or rough sphere or ellipsoid, yeah, right, or a cigar shaped, like a elongated object. That's where the geometry comes. But physically, it goes like cube of the interfacial tension divided by delta G squared. So the important thing I wanted to recognize is this goes like Tc minus T squared. Okay. Yeah. And as you see, the nucleation barrier diverges when the shallow quench. That means what? That means, right, if I plot F dagger versus maybe, yeah, Tc minus T, right? This is going to be like this. This goes up. And it goes all the way to infinity at T equal to Tc. So it diverges. Very strong, the free energy barrier goes up. That means what? This barrier goes all the way to the ceiling where at a shallow quench, right? The barrier goes up. If the barrier goes up, as you know, it's going to take a very long time for the metastability to go away. If the barrier is huge, it'll take enormous amount of time for it to go away, which will work out, right? We'll work out how that appears in a short while. Okay, so instead of this, I could also plot F dagger, right, as a function of a temperature. Temperature goes like this, and then here is my TC, same plot. So if a TC minus T is very large, that means I'm somewhere here, right? Then the free energy barrier is so small, and this is my TC, right? It diverges like this. The same thing, I'm plotting, this is the same as this. I'm plotting the free energy barrier, nucleation barrier goes to infinity at critical temperature. Below that, of course, becomes finite, and how it goes up, right? And how does it depend upon temperature? All depend upon the non-universal details of the system. But this is a very general concept. Okay, so far what I did was I took a droplet, in a spherical droplet. That means the dimension is 3, right? Dimension 3. That's what I worked up. Right. Now, suppose if it's 2-dimension, right? Suppose it's d is equal to 2, right? Then what will happen is this. You'll have the free energy R will go like R square, that's a bulk term, minus R square delta G, forget about the numbers. And then plus, right, a line tension, that will go like a 2 pi R for a disk, that will go like a R times sigma. If you do this, you can do the same calculation that we did, that RC goes like 1 over delta G. It will go like, I can tell you, you can do the work yourself. It'll go like, again, sigma by, when you put all these numbers, sigma by delta G, that will go like 1 over TC minus T. In contrast, right, in very much like what we had for 3-dimensional case. But on the other hand, if you look at the nucleation barrier, that will go like, right, you substitute 1 over TC minus TC, delta G, right? R square will be 1 over delta G square. So what it'll do is, this will go like 1 over TC minus T. This is to be contrasted with 1 over TC minus TD. So basically the formula goes like, right? This goes like, for a 2-dimensional system, as you will see in crystallization, if there is a 2-dimensional nucleation, suppose on a lateral surface of a lamella, and if there is a 2-dimensional nucleation, that is, there's a surface, right there, that's where you are going to grow the new nuclei, new polymer chains, making up lots of stems. Then the nucleation barrier goes like 1 over TC minus T. This is the theorem. You do not have to do very complicated derivations. Physically, by just looking at the problem, you can expect this. Okay, so this is for 2-dimensional case. All right. Then what I like to do is I like to talk about the nucleation rate. Okay, and before I do this, because I think this particular session is going to be over in a couple of minutes, I want to clearly point out, please make sure you follow the distinction between nucleation growth and spinor decomposition. In nucleation growth, there is free energy as a function of the radius of the droplet. That shows this shape. Free energy as a function of radius of the droplet, that shows this shape. And then here, for R greater than RC, the nucleus will grow. For R less than RC, the nuclei will disappear. Okay, this is right. Now in contrast, let's go to spinor decomposition. In the case of spinor decomposition, and what we show is you have the curve is looking very similar, right? But here the physics is entirely different. Here I'm talking about rate of fluctuation, rate of growth of fluctuation. as a function of scattering wave vector k. That is, below some threshold value of scattering wave vector, fluctuations will grow. All fluctuation will grow below this. And then the fluctuation that is going to grow, which is going to have the maximum rate, happens at the Km. So the fluctuations with the wavelengths larger than reciprocal of K, or fluctuation with scattering wave vector smaller than some critical value, they will grow at the cost of the larger K fluctuations, or fluctuation with a lower wavelength, shorter wavelengths. Okay, that's going to come. This is in momentum space, and this is for the rate. In contrast, we have free energy as a function of R. Okay. So what I'm going to do next is I'm going to talk about the nucleation rate. Okay, this is a picture. How do we calculate the rate of growth, rate of formation of the nuclei? Shall we take a small break here? How does it work, Jungfang?
Yeah, Professor, we can have 4 minutes break.
Okay, so I'll take a pause.
Okay.
So the next item that I like to share with you is nucleation rate. Right. Let me give a symbol for this today. That's a symbol. I like to share with you what the assumptions are in getting nucleation rate. Right, because you see these formulas are given in various publications and books, but I think it's important to understand what the assumptions that are being used in the expression that I'm going to share with you. Okay. So let me consider a droplet which has some, I said, radius. Let's say it has n-1 molecules. Instead of R cubed would be number of molecules there, right? It's because the dense droplets object. Right. Therefore, instead of working in radius space, I'm going to work in number of molecules space. Then you could also rewrite it differently if you like. Right. For example, when I write 4/3 pi R cubed, that R cubed means a number of molecules in that system. Then this delta G would be gain in free energy per molecule, right? So you could use any unit that you like. So let's say there are n-1. Then it becomes n. It takes one more. And then it takes one more. It becomes, the droplet gets bigger, n+1. Okay. Let's just look at the growth process like this. I make a droplet above the critical, about some size, not necessarily critical, any size. Well, droplet size n-1, and then I want to look at how it becomes a bigger droplet, and then which becomes even bigger, more bigger droplet. So we write in terms of kinetics, rate equations. So n-1 will make n. Let me say the rate of formation, rate constant, formation of n from n-1, let me write to be n-k, n-1. But this also comes back. This n can also dissolve. Remember when we talked about the free energy landscape, if it's below the critical size, it can dissolve back. So it can also come back. Let me write that to be with a prime, k prime, the droplet of size n loses a molecule with a rate constant k prime. In a similar way, here n becomes n+1 with a rate constant kn, forward rate constant, and then n+1 can dissolve or to lose one molecule to give me N with K prime N plus 1. Okay. And on and on. So I'm interested in figuring out the probability of getting a droplet with N molecules in it at some time T. That's what I'm interested in, right? Probability of getting a droplet of size N at some time T. So the rate with which this is going to happen, dP NT divided by dt, right? This is the rate of realizing a droplet of size N at some time T. That's given by easy, right? Elementary kinetics, chemical kinetics, right? There are 4 steps involved. This can come from here, but it can lose, and it can lose, or it can also come from here. Right. So let's write down the first step. So that is rate constant K, N minus 1, right? That's the forward rate, but depends on the probability of realizing that droplet. So P, N minus 1. I'm not going to write it T, well, I can write it. Okay. That's one step. And the second step is, okay, this is going to lose, right? So therefore I can write minus K prime N P N T. This can lose a molecule to give me, this can lose a molecule, so that will affect the rate of the production of that one, probability of that one. Similarly, I have to write those equations. So now it is depleting N, they're going away, so therefore it will come with a negative sign, K, N, right, P, and T. Then it acquires, right, it can happen, it can appear from this one, right? So that's going to add to this concentration. Therefore, it will be a plus sign, K prime N plus 1, P N plus 1. In the literature, it's called birth-death equation. All right. It's also called master equation. These are all just names. For people who follow the literature, these are all simple, right? If you know the language of how people talk, then everything is simple. Okay. Now, if you look at this one, right, there is a K N minus 1, K prime N, but you know that in reality, all these can be very different, right? And please notice this here, P and T depends upon P N minus 1 T and P N plus 1 T. They're all coupled, but they're coupled locally. One assumption that makes life easy to do the analysis with paper and pencil, right, instead of resorting to computation, is to assume local equilibrium. Okay, so this is an important assumption that we will make. Assume local equilibrium. Some people would call this to be quasi-equilibrium. Okay, quasi, because it's a growing process, right? It's not an equilibrium process. But locally, we say there is going to be a relationship between forward rate constant and backward rate constant. This means what? This means Km, Kn, if you like, forward rate constant, divided by backward rate constant, K prime N plus 1. This is forward reaction, this is backward reaction. You know, the ratio of forward reaction rate constant to the backward reaction rate constant, that's the equilibrium constant for that process. The final product is the initial product. So this ratio gives me the equilibrium constant. That equilibrium constant, as you guys know, folks know, is e to the minus free energy corresponding to the droplet of n plus 1 size minus free energy corresponding to n, droplet of size n divided by kBT. This is your equilibrium constant. Okay, and we know what that is. We know Fn plus 1 and Fn because we can, depending upon the model, we can calculate that free energy in general. Whether you do simulations, whether you do theory, whether you whatever model system you have, we can calculate those quantities as a function of number of molecules in that droplet. So that gives me this ratio. This means, assuming local equilibrium, I can eliminate K prime in favor of Kn. So in these equations, wherever I say K prime, I can get rid of them. Therefore, express K prime in terms of K. Right? In terms of K. So that's good. So that means I don't have to carry, the primes anymore. I'll substitute these values for K prime. So in front of, say, this K prime, I will have an exponential factor like this. In front of this, instead of this, I'll have an exponential factor, corresponding exponential factor like this. Then what we do is we put this in, and then we write this expression. All right? We write this expression, and then if we are talking about molecules, then n and n plus 1 is an incremental change. N is equal to 100, and from 100 I'm going to 100 molecules, so it's an incremental change. So what I can do is I can do continuous notation. I can take n to be a continuous variable instead of having a discrete variable. I can write this to be n. This is n minus delta n. This will be n plus delta n. If you do that, you get the following expression. If you do that, right, so let me make a comment here. Express this, and then plus go to continuous notation. Continuous notation for the variable n. Okay, that's the number of molecules. Continuous notation for this. Okay, if you do this, this gives you the following equation. dp n dt divided by dt is equal to minus d by dn j. J is a flux. That's what we are after. Okay, and that can be written as equal to minus d by dn. This flux, right? That J. I'm going to write that J now. That's equal to minus Kn. Kn is a forward rate constant. Okay. D by dn p nt. Okay. Minus Kn by kt. This is all given to you. The handout is given to you. Okay. dfn by dn. Okay. Then pnt. Okay. So dp by dt is equal to minus the gradient in n space, number of molecule space. J is a flux, right? And that flux is given by this curly bracket term. Okay, so you see the derivative Kn is a forward rate constant that appears here. And Fn, you know, F1 is something you construct. Fn is something for your system, whatever you compose for Fn, that's what that is, right? You get Fn. Okay. And then we have to solve for P and T in general. Okay, so how do we do this? Let's look at, all right, let's look at your free energy landscape again. F, now N. This is with respect to N. As I talked about, it goes like this, right? And I started my system here. That's where I started, at t is equal to 0, right? So for early times, right, I'm trying to look at the nucleation. For early times, the probability that I'm going to find N to be very large, N is somewhere here, that's going to be 0, right? That's going to be 0, right? Because it has not nucleated yet. And similarly, the probability that I'm going to find the nuclei of size which is very close to 1, a small number of molecules is small droplet, that's very high. Okay, so therefore I say during nucleation stage, okay, let's assume T n going to 1 is equal to 1, and P n going to very large number is 0. Okay, and then I want to say, right, and given that initial condition, I want to look for the steady state. Steady state means I want to see what happens. That is, this is 0. In the steady state, it's not, the probability is not changing that much, right? And that means that J is a constant. Because if this is 0, the derivative of a constant is n is a 0, right? So J is a constant. So in the steady state, so these are the assumptions we make, right, in deriving the following formula. In this steady state, J is a constant. And then we call this to be, when that happens, we call this to be nucleation rate. Nucleation rate or rate of nucleation. Okay, let me do this. So it's easy to do. This calculation is trivial to do. If you do that, right, the rate of nucleation, J nucleation, that is rate of nucleation, is equal to 1 divided by an integral 0 to n infinity, because we are talking about continuous notation. Okay, dn and 1 divided by kn. In general, remember kn is forward rate constant, and then e to the fn by kt. Okay, that's the formula, very simple formula. Right, so let me repeat again. So we know we construct free energy as a function of number of particles in the droplet in your system, the new nucleus that you are trying to form, or the system is trying to form. You have that thing. Then the growth rate, there is a rate with which your droplet of size n becomes a droplet of size n plus 1. Okay, that's a forward rate constant. You know, as you can imagine, right, that's going to depend upon n, because the rate with which this is going to take a new particle will depend upon its own surface area, for example, or it could be fractal-like. The nuclei may be fractal-like. So it depends upon your situation. This is going to depend upon n. That k is not going to be independent of n. And that depends upon your system. If it's a lamella that's growing in certain directions, the rate constant would be different. Rate constant to pull one polymer chain to the growth front would be different, right? And et cetera, et cetera. So that's that quantity Kn, that depends on n. And then Fn, you know. So once for your model, if you know what Kn is, you know Fn is, you can calculate is the rate of nucleation. And clearly, Fn will depend upon all the quantities we talked about. Fn will depend upon the, delta G, right? Quench depth. It will also depend upon interfacial tension, surface tension. If I have polymer crystals, which we will return to later on when we talk about crystallization, the interfacial tension between amorphous phase and the crystalline phase, and also the bulk free energy in the crystalline phase, they are all going to contribute describing the nucleation rate. Okay. Now, in terms of the language, I like to make a comment. This equation that I wrote down, dp nt by dt, this is called, I'll use a different color. This is called Fokker-Planck equation. You'll see this in the literature all the time. This is called the Fokker-Planck equation. It's not a magical thing, right? It turns out to be universal. It happens in so many places, so we'll celebrate this equation, right? And we also know how to solve problems of this type, depending upon this Fn, right? How it depends upon n. This equation becomes either easy or complicated. Sometimes you have to do computation using computers. Most of the time, we like to do with appropriate simplifications analytically with paper and pencil. But in general, right, independent of the richness of Fn, in general, what you see is this. Okay, so now what I like to do next is I like to do that integral for you. Okay, and you are probably wondering, how am I going to do this integral? I do not know what this Fn is, right? But I already showed you a picture like this. Fn looks like this. Suppose it's sharply peaked. Suppose this is sharply peaked, right? And, with your experience with doing integrals, we can implement what is called saddle point approximation. You can calculate that, which is given in terms of the position of the free energy at that point. That is your nucleation barrier, right? This is your nucleation barrier. And also the curvature of your barrier. There is a curvature here, how sharp it is. That curvature is given by second derivative of free energy with respect to n at that location, right? Knowing this barrier height and the curvature, knowing that information, you can do this integral. If you do that, you get the following answer. Do that integral, you get nucleation. The nucleation is equal to Kn, right? Kn, that is this 1 over K